So, welcome to this class on hardware security. So, we shall be continuing our discussions on hardware security, and in particular we shall be discussing about power analysis. So, I will be trying to talk about in particular noise as we were discussing in the previous class, and we will try to see how we can statistically analyze the component of noise and try to estimate the success rate of a difference of mean attack. So, in particular, right, as I was discussing in the last class, we essentially have this phenomenon of electrical noise in circuits, which is often due to the power supply, the clock generator, the conduction, and also the radiation emissions from components which are connected to the device under attack. And the idea is that because of the presence of noise, although you are processing the same operation, okay, that is, you are suppose in the context of encryption, you are basically taking the same plain text, the same key, but still you will get slight variations in the power consumption. Okay. And that is a bother for a side channel attacker, because at a side channel attacker you want to get as much noiseless power trace as possible. Okay. Along with electrical noise, you also have another component of noise which is called as the algorithmic noise. So, what is an algorithmic noise? So, let us take this picture of Rindal or AES. Okay. So, this you can easily generalize it to any other target. So, what we do is, as we have discussed, is that in a power attack setting we basically try to do a divide and conquer attack, right. So, we basically try to kind of concentrate on, say, a red portion here as shown here, and this essentially is a component of your for example, or a part of the state. Okay. So, suppose we are doing a power attack from the plain text, we can easily do it or just change the discussion and do it from the ciphertext also. So, here the algorithmic noise or the switching noise occurs because of the contribution of logic cells to the power consumption which are not under attack. Okay. The power trace corresponds to the total power consumption of the circuit. So, that means, like, although you are, say, targeting a specific region or portion of your state, but at the same time the other logic component of the logic cells are also toggling, like they are also consuming power, and therefore, the power consumption, right, essentially takes care, has got both these components. So, it has got a component which I called as the signal, whereas the other components, that means which are not a part of this attack, or we are not considering them in this attack, they are serving to generate noise. This component of noise is called as algorithmic noise, because it basically has got something to do with the algorithm itself. Okay. So, however, as I said that, however, in the attack we target only a small part, see the red circle in the figure, to reveal a portion of the key. Okay. Now, the power consumption from all other parts, so this blue component, for example, essentially forms what is called as the algorithmic noise. So, therefore, you can easily kind of rationalize that this would be more in a parallel implementation compared to a serialized implementation, because in a serialized implementation maybe you will just do one S box at a time, and therefore, you will not have the other S boxes generating algorithmic noise. Okay. So, therefore, right, and I will come back to this point later in our discussion. Okay. So, therefore, right, as I said at the beginning, that for your setup the quality of probes is extremely important. Okay, and they need to be of good of satisfactory quality. So, therefore, right, so observe that as I say, the power consumption of the CMOS based cryptographic devices is an analog high frequency signal, which means that the frequency components are of the power signals are quite high, or could be in like gigahertz range. Therefore, when you are measuring these signals, it could be challenging, because you can immediately understand that when you are transferring the power, okay, power signal from your target to the oscilloscope, there are a lot of things, right, through which the power signal is traveling, and because of that, right, there could be components which are lost. There could be high frequency components which are lost. In particular, right, there could be like when you are propagating from the logic cell on the device to the oscilloscope, there could be factors like filtering because of these channels. There could be crosstalks, there could be thermal noise. Okay. And the parasitics in this mentioned path essentially serves as a filter. They basically limit the bandwidth. Okay. For example, you can have the bypass capacitances, or you can have the inductances. All these things will play a role to basically like serve as like sort of like a band pass filter. They will basically like kind of remove some of the high frequency components. So, therefore, the probes of the oscilloscope should have a bandwidth of more than 1 gigahertz as a thumb rule, and typically less than 4 picofarad of capacitive loading. Okay. With such settings, you can get a high bandwidth part of the power traces to propagate without any degradation. So, this is an important thing that we need to take care of when we develop our side channel setup. So, again like I said that so let us try to look again at the power traces, but now from the point of like trying to develop a statistical analysis. Okay. So, electrical noise, as I said, of a power trace can be characterized, right, typically. So, this is a very important component, like when you are considering the power consumption, your power is kind of superimposed, right, with a component from the noise or the electrical noise. Now, this component of noise, which is the electrical noise, typically can be modeled by a Gaussian distribution. Okay. So, therefore, right, you can see that you have you can basically kind of define it by a mean, which is mu, and a variance, which is sigma square. And as you know that from statistical theory, that you try to develop estimates for these parameters. Okay. So, for example, right, average or x bar is like is essentially an estimator which is used for mean, and likewise the empirical variance or S square is used as an estimator for variance or sigma square. Now, for some fixed value an operation, right, as I said, the power consumption is fixed except for the variance that is introduced by the electrical noise. So, therefore, right, when I am keeping my plain text and my input key, for example, same, then I would expect that the component which is essentially that is the real signal, that means the power consumed due to the actual processing of information, that is a constant. Okay. Whereas the other components essentially, or like the electrical the noise basically essentially tries to kind of develop the variation. I mean, the variation is coming because of the noise. Okay. And therefore you will see that if you plot at a specific time instance, if you basically try to plot the power consumption, although you are keeping keeping the plain text same and the key same, you will find out there is a variation, and you will see that the variation looks like a Gaussian distribution or a normal distribution. Okay. So, this diagram shows like again that you are basically trying to obtain the power traces of AES, and you can see that all of them looks roughly same, but there are small differences. Okay. So, therefore, the question is why is that difference, and the answer is because of electrical noise. Okay. You have got slight differences. Note that this component, right, is not due to algorithmic noise, because the in the algorithmic noise should not differ, because you are keeping the data same in both in all these cases. Okay. So, therefore, right, how does it look like? So, therefore, the total power at a time t typically has got two important components. One is p data, which is the power consumed at time t due to the data dependent component, and the other part is a noise component. So, I am assuming that you are doing the same operation. Okay. So, in that case, right, there is no operation dependent component, but rather there is a data dependent component, because the data is changing although you are doing the same encryption again and again. Okay. So, and the other thing is the noise. So, this noise essentially you can see that like essentially has got a Gaussian distribution, and because of which, right, the power consumption also takes the Gaussian shape. So, for example, here we plot the power trace, okay, at a specific instant of time. So, essentially we see that so in this case, for example, this adjacent histogram shows the distribution of total power at a given instance of time for say 1000 encryptions with the same input and key. Okay. And you can observe that the normal distribution is quite evident, right. You see that there is a nice normal distribution where you can fit your histogram. Okay. So, this is the histogram, the green bars are the histograms, and we have fit in a normal distribution to it. Okay. So, this normal distribution shows the distribution of electrical noise, and just to recapitulate, this is how a normal distribution looks like. This is the density function for the normal distribution. Now, the density function describing the normal distribution depends upon the parameters mu and sigma, the mean and the standard deviation. Of course, the mean can be anything between minus infinity to plus infinity, and the sigma is essentially greater than 0. Okay. And you can write the usual way of saying that x follows a normal distribution is by using this notation, and n and the parameters are mu and sigma, and if you say so, then it implies that your density function f x, right, is essentially given by this equation. Okay. That is 1 by root over 2 pi sigma in the denominator exponentiation to the power of e to the power of minus 1 by 2 x minus mu by sigma whole square. Okay. If mu is 0 and sigma is 1, then we call this as a standard normal distribution, and the cumulative distribution function of the standard normal distribution is denoted as phi x. That means, like if I integrate, for example, and I try to find out like the entire, say suppose I draw a specific I draw a straight line here which is for a specific value of x, and I try to find out, basically add up all of them, like till that value x, right, then essentially I get the cumulative value, and that distribution is often denoted as by the notation phi x. Okay. So, the points in the power trace follows a normal distribution, and the normal distribution is also called as the Gaussian distribution. Okay. So, we can also use these words interchangeably. We can say sometimes normal distribution, and we can sometimes say Gaussian distribution. So, now what is the sampling distribution? So, the average value and the standard deviation, suppose I am trying to estimate them, okay, that means I am basically say like getting 1 sample, 2 samples, 3 samples, and I am trying to kind of estimate the corresponding average value, okay, and also the standard deviation. Now, this would change every time, right, you are doing the experiment or redoing the experiment, these values will differ. Okay. So, you can view them, the average and the empirical standard deviations, therefore, as random variables, and the mean value and the empirical standard deviation can be characterized again as a probability distribution. Okay. So, that means, and this concept is what is called as a sampling distribution. Okay. So, the sampling distribution determines often how well a certain parameter can be estimated. Okay. So, we try to develop sampling distributions for say mean, okay, and then the sampling distribution for mean would probably look like this. Like suppose in a case of average, the value x bar, which is a sampling distribution, in this case determines how well the average value estimates mu. Okay. So, we know that if I take large number of samples, then by the law of large numbers, this will tend to mu, but of course, with finite values it will not be exactly mu, but it will start approaching mu. Okay. So, the sampling distribution of x bar is a normal distribution, and it is denoted as x bar follows normal distribution with the mean same as mu, but the variance becomes sigma by square root of n. This also shows that when you are increasing the value of n, then sigma by square root of n is getting smaller and smaller. That means, you are basically approaching, the average value is getting close to the mean value with more and more measurements, with more and more observations. Okay. So, therefore, for normal distributed values, we know that the average is a very good estimator for mu, and with more traces, more trace estimations becomes better, and the average value is tending more towards the objective, towards the value of mu. Okay. So, now another important concept which is required to understand the following concepts is essentially what is called as the confidence interval and hypothesis testing. Okay. So, the quantity basically says how close a certain approximation is to a real parameter, okay, is often defined by confidence intervals. See, this is a very important concept, because when we are doing a difference of mean attack, we need to predict the mean, right. So, therefore, this is the parameter which you are trying to estimate, but then the question would be how many observations you need to estimate it with a high confidence. Okay. And that is where this concept of confidence interval comes in, because it tells us that it basically is a quantity or defines a quantity which tells how close a certain approximation is to a real parameter. Okay. So, when we say, for example, that we have got a 0.99 confidence interval for mu, we mean to say that we have an interval that contains mu with a probability of 0.99. Okay. That means, we are saying that there is an interval which kind of engulfs mu with a high probability. Okay. And hypothesis testing is a statistical tool to define this confidence interval. Okay. So, in such tests, what we do is as follows. We basically test whether we basically make a hypothesis. Okay. So, hypothesis would be essentially a claim about the parameter or parameters. Okay. And for example, we want to test whether mu is equal to mu 0 or whether mu is not equal to mu 0. Okay. So, what we do is that we basically make two hypotheses. One is a null hypothesis denoted as H0, described as mu equal to mu 0, and there is an alternative hypothesis which is mu is not equal to mu 0. Okay. An important point which can be mentioned here is that the null and the alternative hypothesis, although in this example are complementary, okay, it need not be complementary. They are not necessarily complementary. Okay. That means, they are not necessarily exhaustive, but they are exclusive. Okay. That means, they are mutually independent. They are different. I mean, they are, rather than saying independent, it is better to say that they are exclusive. Okay. So, now, so let us take our example. So, this is our power trace, for example. So, we basically had we have basically fitted that into a normal distribution, and we would like to convert this into a standard normal distribution. Okay. And as I said that in a standard normal distribution, you have got the mean as 0 and the standard deviation, right, or sigma essentially as 1. Okay. Therefore, the normal distribution is 0, 1. So, now the usual way of transforming that is that suppose you have got the sampling distribution for mean denoted as mu sigma by root n, as we have seen in the previous slide. We will make a transformation from x bar. So, we will basically substitute x bar as x bar minus mu into square root of n by sigma. If you do this transformation, then you get z, and this z essentially will follow a standard normal distribution, which means it will follow n with mean as 0 and standard deviation or sigma as 1. Okay. So, now we would like to develop or find out the characteristic of a standard normal distribution, which we will be using in our hypothesis testing. So, this is the standard normal distribution curve. Now, this particular curve has got some important properties. Okay. These properties are typically, right, essentially very important and central to the understanding of hypothesis testing. Okay. And they are essentially described by something which is called as Z alpha or what are called as quantiles. Okay. So, let us see what they mean. The idea is that if you take the area under the curve would be essentially 1 or unity. Okay. And here you will see that there are certain notations which are called as Z alpha, and as I said, the cumulative value, which is essentially phi of Z alpha, indicates the probability that the Z statistic takes a value which is less than or equal to Z alpha. So, P Z less than equal to Z alpha is nothing but phi of Z alpha, and that is equal to alpha in this particular curve. Okay. And also note that Z alpha is equal to minus of Z 1 minus alpha, because it is kind of symmetric over the 0 value. Okay. So, this is the 0 line, because the mean is in this case 0. So, we have got Z alpha equal to minus of Z 1 minus alpha. Okay. So, this you can easily check from the normal distribution curves. Okay. And so, now that implies that if I take a region from Z alpha by 2 to Z 1 minus alpha by 2, then the probability that Z will lie from Z alpha by 2 to Z 1 minus alpha by 2 is equal to 1 minus alpha. That is because if you take Z 1 minus alpha by 2, then the probability that it is less than Z 1 minus alpha by 2 is, so for example, right, if you take alpha by 2, the probability that it is less than Z alpha by 2 is alpha by 2. Okay. And as we know that from here Z alpha by 2 is equal to minus of Z 1 minus alpha by 2, and by the symmetricity we know that the probability that it is greater than Z 1 minus alpha by 2 is also alpha by 2. Okay. And as I said that since the area under the curve is 1, that means the probability that Z will lie in this region, that is from Z alpha by 2 to Z 1 minus alpha by 2, is nothing but 1 minus alpha by 2 plus alpha by 2, that is 1 minus alpha. Okay. So, therefore, right, what we will see, why there is a reason why we call alpha as the error probability. I will explain very soon why, but you can but rather let me state here that this region or this closed region from Z alpha by 2 to Z 1 minus alpha by 2 is called the confidence interval of Z with a confidence of 1 minus alpha. Okay. So, now this like the statistics of or the properties of this standard normal distribution is often described by a table. Okay. So, here is a small summary of the table, but there are more data that you can easily get from a bigger table. For example, like if I take alpha, and if the alpha value is 0.975 for example, then the corresponding Z alpha is 1.960. Okay. So, I hope now we understand that what it means, because this follows from this fact, okay, that is P Z less than equal to Z alpha. That means, if I take a value of alpha like 0.975, that is 0.975 somewhere here, then the if your Z alpha is for example 1.960, then I would basically draw a line here through this point, that is 1.960, and that would imply that the probability that Z is lesser than this, that is it lies on the left hand side, is given by this value which is denoted by alpha. Okay. So, for example, the alpha value is 0.975. Okay. So, therefore, the quantiles essentially defines this probability distribution, okay, and which we will be using in our hypothesis testing shortly. So, let us try to define now the confidence interval for mu, okay, which we are trying to estimate. So, as I said that z essentially follows a standard normal distribution curve, where z is equal to x bar minus mu into root n by sigma. So, that would imply that we are basically trying to limit z between z alpha by 2 and z 1 minus alpha by 2, right. That is the confidence interval that we just now saw here. Okay. So, now using this, right, we basically write this equation, and that implies that I can now like do a few simplification. I can multiply both these sides by sigma by root n. Therefore, I have got sigma by root n z alpha by 2, which is less than equal to x bar minus mu is less than equal to sigma by root n into z 1 minus alpha by 2. And again, right, since I want the confidence interval for mu, I bring in, I do a little bit of maneuvering, and therefore, I see that mu is bounded between x bar minus sigma by root n z alpha by 2, and it is also lower bounded by x bar minus sigma by root n z 1 minus alpha by 2. Okay. Now, note that z alpha by 2 is nothing but minus z 1 minus alpha by 2. So, therefore, I can replace this z alpha by 2 by minus of z 1 minus alpha by 2, and therefore, I get that mu is bounded between x bar minus x bar plus minus sigma by square root of n z 1 minus alpha by 2. Okay. So, therefore, my confidence interval for mu with a confidence of 1 minus alpha would be x bar minus sigma by square root of n z 1 minus alpha by 2 to x bar plus sigma by square root of n z 1 minus alpha by 2. So, now once we have derived this confidence interval, we are all set to understand what is hypothesis testing. So, as I said that if you want to test that whether mu equals to mu naught or not, or whether mu is equal to mu naught or mu is not equal to mu naught, you make two hypotheses. So, you state two hypotheses. The null hypothesis is that mu is equal to mu naught, and the alternative hypothesis, or H1, is mu is not equal to mu 0. So, now we estimate mu by calculating the average value x bar, because we do not know what is the actual value of mu. So, now the idea is that if x bar minus mu naught, okay, mu naught is the value that you are trying to see whether mu is equal to that, and if you find out that this empirical mean, right, that means the absolute value of this error is much larger than some predefined constant. So, this predefined constant is often given beforehand depending upon the accuracy or precision that is required. Then we will reject H0, because that means that it is too big than allowed, okay, or than possibly, and that possibly means that x bar is not mu naught, okay, or I mean rather mu is not equal to mu naught. Else, that means if it lies inside this region, then we accept H naught, we accept the null hypothesis. So, this constancy is vital again, and it defines what is called as the critical region, the region where the null hypothesis is rejected, because if it lies in this region, it is much larger than this constant c, then and it lies in that region, then you are basically rejecting the null hypothesis. Okay. So, therefore, right, this brings us to the fact why alpha is called as an error. You remember that I called alpha as an error. So, it is because of this fact that it basically is nothing but the false positive error. Okay. So, it may happen that the null hypothesis is true, but we reject it, and this is called as a false positive error. Mathematically, the probability of this event is nothing but p x bar minus mu naught absolute value greater than c, and that is equal to alpha. Okay. So, that is why alpha is called as the error probability, and what we want often is that we will try to reduce this error probability, and if we do that, then that implies that 1 minus alpha will get increased, and therefore, the confidence will get increased, okay, and that is intuitive. That is why you are reducing error and you are increasing your confidence of estimate, okay, and that is understood. So, therefore, if alpha reduces, then confidence increases. So, now we are all set to understand or estimate the number of traces to estimate mu. Okay. Suppose we need to estimate the mean with a precision say 0.01. Okay. So, say p of, so as I say that p of mod x bar minus mu naught is greater than c, this is equal to alpha, this is your error probability. Alternatively, that means that probability that x bar minus mu naught is greater than c, you can also write that by multiplying both sides by root n by sigma. Note that sigma is positive. So, you can multiply them without changing the sign, and this is nothing but your z, right, or the absolute value of z, which is your z statistic. Now, the absolute value of z is basically greater than C square root of n by sigma. Okay. And this means that this probability, right, if we just remove this absolute sign, then that means that this is nothing but 2 into probability of z greater than equal to C square root of n by sigma, okay, and that is equal to alpha. Okay. So, this is an important thing to understand. So, I hope that it is clear. So, let me try here to explain this point. And so, basically what I am trying to say is that this is your normal curve, right, and you are basically trying to say that when you are saying that mod z is greater than this parameter, then that means you are bothered about the absolute value of z being greater than this. Okay. So, that means you are basically bothered about both these regions, this region as well as this region, because the absolute value is important. Because when you are writing this fact, that is z is greater than this, you are only writing this region. So, in order to account for that, you basically bring in this factor of 2. Okay. So, you bring in this factor of 2, and therefore, write p z greater than C square root of n by sigma is equal to alpha by 2. Okay. And that implies that this is nothing but z 1 minus alpha by 2. Okay. Remember, right, that this essentially, as I said, that if this is z 1 minus alpha by 2, then the probability that it is greater than this was shown to be alpha by 2. Okay. So, therefore, right, we can essentially write that this parameter, that is C square root of n by sigma, is nothing and equated nothing but z 1 minus alpha by 2. Okay. And this immediately tells me that n is equal to sigma squared by C squared into z 1 minus alpha by 2 whole square. Okay. So, this gives me a closed form expression of estimating the number of traces which are required to estimate the value of mu. Okay. So, what we will see next is we will see few more like inferences on this and try to see how we can apply this on like on getting the difference of mean attack analyzed in a much more predictable fashion. Okay. But we will take that in the next class.